So what we're going to look at today to start with is just a couple of little basic properties of some improper integrals, which are going to sort of get us into some of the ideas that we need to start thinking about when we do start talking about series. So one is that if we have two functions, we'll call them f and g, both of them continuous from some value a to infinity, where they're both positive functions, and they're both always positive between a and infinity, and f is always less than or equal to g on that interval, then we could be guaranteed that f will converge if we know that g converges. So that should be, I think, fairly straightforward to think about. Here is some function, let's call it g of x, and we'll call this a. Here's g of x, and here's g of x. And let's say they both share this same point. First point, let's see if I can get myself the tools up here and get a different color, but it probably won't work because my brand new district laptop for this year is garbage. Oh wait, no, I didn't say that on the recording, did I? Oh no. It's not going to give me my tools. Oh well. All right, so suppose then here is, oh, that was terrible. Suppose there is f of x. And they don't have to share that point in common, but they happen to. If we know that g converges, then we must also know that f converges, right? Because if g converges to some numeric value, it's not infinite, then something that's always less than or equal to it will also converge to some finite value. It's not going to converge to the same finite value. It might converge to some, it's going to converge to some value less than g of x, or less than or equal to, supposing if g of x and f of x were the same function. But f of x should definitely converge. Would you all agree with that?
Mm-hmm.
Yeah. Okay. It's I think pretty obvious then that the opposite of that would be true, that g must diverge if f, the one that's below it, diverges. So if f diverges, if we can prove that f diverges, we can be guaranteed that g diverges. And if we can prove that g converges, we can be guaranteed that f converges, which is a sort of helpful little trick to help us determine if certain functions converge or diverge as they go towards infinity, because there are some functions that we may not be able to actually integrate. So conceptually, everybody okay with that?
Yes.
Okay. So what I want to know then is, does the integral from 1 to infinity of e to the negative x squared dx converge, or does it diverge? So that's our goal. We want to figure out if this converges or if this diverges. Anybody know how to integrate e to the negative x squared? The answer to that question is no, none of you do, because there is no explicit function that represents the integral of e to the negative x squared. It's one of those fun functions that you just can't integrate. And so there's no way for us to write this out as an improper integral, do a limit as a approaches infinity of the integral from 1 to a of this function if we can't actually figure out the integral of that function and then evaluate that limit. So we're going to have to take some function that is related to this function, perhaps, that we can compare it to and determine if that function that we should hopefully know how to integrate converges or diverges, and that should help us to determine if this one converges or diverges. Sound good? Does that conceptually make sense what we're going to try and do here?
Yeah.
All right. So that being said, what's a function that from 1 to infinity, you could relate to this one, that's maybe similar to it? Any functions you want to try that we do know how to integrate? Okay, I got an e to the negative x from somebody and an e to the x from somebody. So e to the x is we'll talk about e to the x first. E to the x is a real simple one. If we tried to plug in e to the x, you meant e to the negative x, Derek. Okay, never mind. All right, we got two e to the negative x's. All right, so let's look at e to the negative x. That's a good choice. So let's think about what happens on the interval from 1 to infinity. The relationship between e to the negative x and e to the negative x squared. So what could we say between those? Is e to the negative x always less than or equal to e to the negative x squared, or is always greater than or equal to e to the negative x squared?
Should be always greater than or equal to, right?
Should be, right? Because we think about this as this is 1 over e to the x, right? Or this is 1 over e to the x squared. And if we're plugging in x values that are getting larger, then the x squared is getting larger, which means that the e to the value is getting larger, which means our denominator is getting larger, which means that value is getting smaller. So the e to the negative x squared has got to be smaller than or equal to e to the negative x from 1 to infinity. Everybody follow that logic?
Yeah.
Okay. So then if we can show that e to the negative x converges, then we should be able to show that e to the we would be guaranteed that e to the negative x squared, which is always less than or equal to e to the negative x, will also converge. But if we go through and we do e to the negative x and find out that from 1 to infinity e to the negative x diverges, then this has been no good to us. And we'll have to go in and try a different function. So how do we find the integral from 1 to infinity of e to the negative x dx?
By using as a constant b approaches infinity of 1 to b.
What variable did you say you want to use?
B.
B. Okay, the limit is b approaches infinity of an integral from 1 to b of e to the negative x dx then. Okay, and what's the integral of e to the negative x?
Negative e to the negative x.
Okay, so we got the limit as b approaches infinity of negative e to the negative x, and we'll evaluate that from 1 to b, which ought to give us a limit as b approaches infinity of negative e to the negative b minus negative e to the negative 1. And as b goes towards, that's the worst infinity I've ever drawn, that's better. As b goes towards infinity, negative e to the negative b becomes what? It should be 0, right? And then negative e to the negative 1 should be 1 over e. And I mean, great, that value is 1 over e, which tells us that this integral converges. And so then we will say, since the integral from 1 to infinity of e to the negative x dx converges, the integral from 1 to infinity of e to the negative x squared dx also converges. And in fact, we know that it converges to some value that is less than 1 over e. Good or no?
Yeah.
So I just a little trick that can sometimes be used to kind of find out information about a function that we might not otherwise be able to figure out. So this is something that we're going to use, this idea of one function being greater than or equal to another function. We're going to use that idea in series to prove a lot of different, to prove that a lot of different series converge, or to also prove that some series might diverge. So just keep that in the back of your head over the next 2.5 months because we're going to use it again. All right, let's do an arc length problem. We're going to use the arc length formula just for fun here to show that the circumference of x squared plus y squared equals 16 is 8 pi, which we should know because we know that that's just a circle with a radius of 4. And so its circumference should be 2 pi r, but let's prove that's true. So how are we going to do that?
What if we converted it to polar and then like took the polar arc length?
Okay.
Because that might be easier. I don't know. It's just kind of a messy
Sure,
integral.
we could give that a shot. So let's see what happens if we do that.
So it's just r equals 4.
Okay. So r equals 4, then what does x equal?
4 cosine theta.
And what does y equal?
4 sine theta.
Okay. And how do we find the how do we find our arc length using polar coordinates? What do we need? We need a dx d theta, right? What's dx d theta?
Or sine theta.
It is.
I don't.
Negative 4 sine theta.
Negative 4 sine theta sounds better.
Oh, d. I was thinking integral. Sorry.
Yeah, that's all right. And what's dy d theta? Should be 4 cosine theta. All right, so what do we get then when we try to do this? We get an integral from where to where?
Probably 0 to 2 pi.
Okay, we could try that, 0 to 2 pi. Could also break it down to 0 to pi over 2 and do 4 of them, or some other integral like that, right? But 0 to 2 pi should be fine, right? And what do we have? We have a square root, and it should be dx d theta squared, so 16 sine squared theta plus 16 cosine squared theta d theta. Good or no? What does that give us?
4.
Wow, if we take the 16 out, it should give us a 4, right? And then sine squared plus cosine squared is 1, square root of 1 is 1, so just a d theta there. Yeah. And then what? What do we get? Yep, we just get 4 times theta from 0 to 2 pi. Works out real nicely that way, huh? 8 pi. Yeah, just 8 pi units. And I was thinking we were going to do it a different way. We could have left it in our rectangular coordinates, and then we would have had to use an improper integral, which is what I was going to do to practice for tomorrow's quiz. But that's fine. This is nice and simple and straightforward. And I won't make you do this on the quiz, so we don't need to go back and do it the other way. If we wanted to do it the other way, you just have to solve for y equals the square root of 16 minus x squared. Right, and then you'd find your derivative of that and do your integrals. It ended up requiring a trig substitution. It would come out to look very, very, very similar to what we ended up with here at the end. So. All right, let's apply these improper integrals into volume. So suppose we want to find the volume of the solid that can be obtained by taking the curve y equals x e to the negative x from 0 to infinity and revolving that around the x-axis. And so just for fun here, maybe not just for fun, but just because I think it's good to look at it, let's put in our graph x e to the negative x, which looks like this. And so if we're going to go from 0 to infinity, we can see that we're going to have this, as this whole thing revolves around, we have a, we're going towards infinity. So we're going to maybe have an infinite volume, but potentially it might converge to have a finite amount of volume if we were to do this. So this is what we're revolving around. We're just going to use what method, since our region is fully pushed up against the x-axis the whole time, revolving around the x-axis. What method will we use?
Just taking the area of the circles.
Yep. So we should do pi times our integral from 0 to infinity of just our radius, which is just our function, x e to the negative x squared dx. And what do we have to do with this in order to evaluate this integral?
Probably do it by parts, right?
Yeah, but before we can do the integral, it's an improper integral. So what do we have to do with it?
Oh yeah. It would pi times the limit as b. I'm just going with b every time. Approaches infinity.
B approaches infinity of the integral from 0 to b of x squared e to the negative 2x dx. Everybody agree there? Yes, no, maybe. So x squared e to the negative 2x, as I think you said a minute ago there, we should do this by parts. And we can use a trick for this one to do this one by parts, right? Because one of the pieces of it will differentiate down to become 0. So we can use tabular integration here. So derivative of x squared is 2x, derivative of 2x is 2, and the derivative of 2 is 0. And what's the integral of e to the negative 2x?
Negative 1/2 e to the negative 2x.
And the integral of that should be positive 1/4, right? And then the integral of that should be negative 1/8. All with e to the negative 2x attached to the end. Everybody good with that? Yeah, maybe? No?
Yep.
Okay. And so we'll attach those two together, and those two together with a positive, negative, positive, right? So we should end up with pi times the limit as b approaches infinity. Our integral should now become negative 1/2 x squared e to the negative 2x minus what? Minus 1/2 x e to the negative 2x, and then minus 1/4 e to the negative 2x. And we'll evaluate that from 0 to b. Good or no?
Yeah.
Wonderful. All right, so now we've got pi, we got our limit as b approaches infinity. Now we got to write all this nonsense out. So we got negative 1/2 b squared e to the negative 2b minus 1/2 b e to the negative 2b minus 1/4 e to the negative 2b minus, plug in 0 to this term, you're going to get 0. 0 to this term, you're going to get 0. And 0 to this term, you're going to get minus 1/4. Everybody agree there?
Yeah.
Okay. And as b goes towards infinity, what happens to each of those e to the 2 or negative 2b's? They all drop to the denominator, right? Because of the negative 2b, and that means that we have a quadratic over an exponential, and then another linear over an exponential, and then we have a constant over an exponential. So each piece of these, as b goes towards infinity, this will approach 0, this will approach 0, and this will approach 0. And therefore, we just end up with minus 1/4. Not sure why I'm sort of missing that. There we go. And minus 1/4 is a fourth times the pi, which gives us pi over 4 units cubed. So there is a finite amount of volume, even if we take an infinitely long curve and revolve it around the x-axis, we have only a finite amount of volume, pi over 4 cubic units. Pretty cool.
This is very cool.
Yeah. All right. So we're going to do a little bit of investigation here. So first off, I want you guys to take just a minute here and find the area underneath the curve 1 over x from 1 to infinity. We may or may not have already done this, but just real quickly, take like a minute and do this improper integral. All right? Ready to go. All right, so we wrote this out as a limit as, I'm going to use a this time just to annoy Noah. Limit as a approaches infinity of the integral from 1 to a of 1 over x dx, which gives us a limit as a approaches infinity of natural log absolute value of x from 1 to a, which gives us the limit as a approaches infinity of natural log a minus natural log 1, which is natural log of infinity minus 0. And clearly, as the natural log function, the x values go towards infinity, this becomes infinite. And so we will say, what about this amount of area? It is infinite, right? And we would say that this integral diverges. So this is a divergent integral telling us there is an infinite amount of area. Would you all agree with that?
Yeah.
Great. Okay. Very important that we recognize and accept that underneath the curve 1 over x, from 1 to infinity, there is an infinite amount of area. All right. Now, I want you to, well, we'll do this together, just for fun, not that it's difficult. But let's take that exact same region that has an infinite amount of area, and let's take it and revolve it around the x-axis, which means we're going to set this up instead of just as an integral from 1 to infinity of 1 over x, but it'll be pi times the integral from 1 to infinity of the square of 1 over x, which ought to be 1 over x squared dx, which should be rewritten as pi times the limit as, once again, I'm going to use a, as a approaches infinity of the integral from 1 to a of 1 over x squared dx. And what's the integral of 1 over x squared?
Negative 1 over x.
Perfect. Negative 1 over x. And we're going to go from 1 to a, which will give us pi times our limit as a approaches infinity of negative 1 over a minus negative 1 over 1. And as a goes towards infinity, negative 1 over a, negative 1 over infinity is 0, plus 1, which gives us pi units cubed. True? Would you all agree with that? Or no?
Yeah.
Yeah. So there seems to be something slightly paradoxical going on here, right? That there is an infinite amount of area underneath it. But if I take that region that has an infinite amount of area and I revolve it around the x-axis to make an infinitely long little cone-looking thing, which we're going to talk more about in a second. It's not really a cone, but it has a finite amount of volume, which seems a little bit weird, doesn't it?
It absolutely does.
Yeah, but pretty darn cool. Math is kind of amazing that way. Now, we're going to do something here that is not part of what's required for the AP test. I'm gonna introduce another formula. There's a way to find the surface area of a solid that you've revolved around an axis. So this is the formula, and we're not going to go into the derivation of it because we don't need to, and we don't need to do this for the AP test, but you'll see that it's very, very similar to what we're looking at when we have our arc length, right? Except we've got a 2 pi out there. And we get 2 pi times the integral from a to b of now our function times the square root of 1 plus the derivative of our function squared. Okay, so this gives us the surface area if you take a solid and rotate it around an axis. And so what we're going to do is we're going to use this formula to find the surface area of that same function 1 over x from 1 to infinity. And so we're going to see, I don't know, it's either going to be a finite amount of surface area or it's going to be an infinite amount of surface area. It's either going to match up with the area or it's going to match up with the volume. So that'll be an interesting thing for us to look at, find out, don't you think? Yeah, you do.
Really?
Yeah, so let's do 2 pi times the integral from 1 to infinity of our function, which is 1 over x. So put a 1 over x there. And this would be a good practice for us on some of our integration techniques because we want to see if we can do this all by hand. 1 plus, well, let's see. What's the derivative of 1 over x? F prime of x is
negative 1 over x squared.
Negative 1 over x squared. And so f prime of x squared ought to just be 1 over x to the 4th dx. Everybody good there?
Yeah.
Okay. And since this is an improper integral, what are we going to need to do? We're going to want to rewrite it as a limit. So we're going to say this is the same as 2 pi times the limit as, just for you this time, no, we'll go back to b approaching infinity of the integral from 1 to b of 1 over x. And we've got 1 plus 1 over x to the 4th. And I think it might be better for us if we were to combine the fraction and the whole number in there into just a single rational function inside the square root. Oftentimes that's a good technique. So I'm going to multiply the 1 by x to the 4th over x to the 4th to give me x to the 4th plus 1 over x to the 4th dx. Good or no?
Yeah.
All right. This we should be able to simplify a little bit further. Now, 2 pi times the limit as b approaches infinity of our integral from 1 to b. And what part of that thing can I simplify that's inside my square root?
The over x to the 4th part.
Right, the over x to the 4th. I can just pull that completely out of the square root, right, and just put my square root only in my numerator. And what will my denominator now be?
X cubed.
Should be x cubed, right? Everybody good there? Or no?
Yeah.
All right. Thoughts on what we should do next then?
Can we just use sub at this point?
What are you going to use sub?
I was thinking the thing under the square root, but I
Yeah, so that's
haven't
the
actually
problem,
tried
isn't
that
it?
yet.
Yeah, it's a reasonable thought, but if you try to take out the x to the 4th plus 1, your du would be 4x cubed, which is great because there's an x cubed, but the problem is that x cubed is in the denominator. You need that x cubed to be in the numerator, which is just going to end up complicating things a little bit more. Well, what's one of our new techniques for integration that we learned this year? What's the first new technique, in fact, that we learned this year for integration?
try inverse trig substitution?
That's not the first one we learned. We're going to have to do that eventually, but not yet. It's a good idea, right? This x to the fourth plus 1 sort of looks like something we could. We wouldn't be able to do like x equals tangent theta, but we could do x squared equals tangent theta. But the problem with x squared equals tangent theta would be something like, well, now I have this x cubed down here, and that's going to be tangent to the 3/2 power. That's going to be an issue. So we're going to have to do something else. Inverse trig subs was not the first technique we learned. What was the first technique we learned?
Should we do integration by parts?
Yeah, let's do this by parts. So what do you want u to be? Probably the more complicated thing that we can take the derivative of, whereas dv should be the most complicated thing that's easy to integrate.
Yeah.
So
1 over should be dv.
Yeah, 1 over x cubed dx will be our dv, and our u will be root x to the fourth plus 1. Giving us du is what? 4x cubed in the numerator over 2 root x to the fourth plus 1 dx. And what's our v going to be? Should be negative 1 over 2x squared. Everybody agree with that?
Indeed.
All right. I think we have run out of room here. So we are still going to have a 2 pi. We're still going to have a limit as b approaches infinity. We're still going to have an integral from 1 to, actually, we won't have our integral from 1 to b yet. We'll have our u times v first. And let's see. I know our u was the root x to the fourth plus 1. Our v was what? Negative 1 over 2x squared. So negative root x to the fourth plus 1 over 2x squared. Let's do this. That's got to be evaluated from 1 to b. And then we're going to add to that our VDU, which should be what? If we simplify out that VDU, what do we get? We should end up with just an x in the numerator, right?
Yes. Negative x over root x to the fourth plus 1.
Yeah, sorry. I did that negative already. So we had a negative, right? And then the other negative that's inside of that will make that a positive. And so that'll be x over root x to the fourth plus 1 dx. Good or no?
Yeah.
Wonderful. All right. Then what?
Well, now we should probably do, or the trig substitution would probably work pretty well for that.
Okay, so if we want to try to do the trig substitution here, we can let x squared equal tangent theta, which will tell us that 2x dx equals secant squared theta d theta. And what is that going to give us then? We need to put a 2 in here, and we need to put a 1/2 in there. And then we should be able to replace all of that junk in that second integral we've got now and put it all in terms of trig functions. Sound good? So we got 2 pi times the limit as b approaches infinity of, I guess I'll just leave this as is for now, negative root x to the fourth plus 1 over 2x squared from 1 to b. We'll write that out all the way in a minute. Plus, and then this now is 1/2 of the integral. And I'm not going to worry about my limits here. I'll deal with those in a second. What do we get here? We have 2x dx, which should become secant squared theta d theta, over root x to the fourth plus 1, which should become root tangent squared theta plus 1. And I think that if x squared is equal to tangent theta, but we've got 1 and b in here, that's going to be a pain to deal with in terms of theta. So I think a better option here is just to stick with calling these x equal 1 and x equals b. And once we've evaluated this integral in terms of theta, we can just convert it back into terms of x to evaluate. Does that sound reasonable to everybody?
Yes.
Okay. And if it comes through and the integral makes it easy to do by turning these into theta as we can, but for now, let's stick with how we've got it here. So we've still got 2 pi. We've still got a limit as b approaches infinity. We've still got negative root x to the 4th plus 1. Still got our 2x squared in the denominator. We still got a 1 to b. And now we've got what here? We've got plus 1/2 of our integral from x equals 1 to x equals b of, what does that turn out to be? Square root of tangent squared theta plus 1 is secant squared theta, square root of secant. So we've got secant squared over secant, which is secant. So we just got the integral of secant theta d theta. Good or no?
Yes.
All right, perfect. So now we've got 2 pi times the limit as b approaches infinity of negative still root x to the 4th plus 1, 2x squared, still 1 to b. It's a fun little integral, huh? Plus 1/2 natural log absolute value secant theta plus tangent theta. That being our integral for secant theta. And now this is all going to be evaluated from 1 to b. So now I think we're ready to evaluate. Yeah?
We should.
Well, no, we got to start x equals 1. X equals 1 to x equals b. We still got to convert those thetas back. And so if we're going to convert those thetas back, triangle might help us. Right? Here's theta. Tangent of theta is x squared, so that's going to give us an x squared and a 1, which is going to give us a root x to the 4th plus 1 here. I think the visual will help us to write out secant and tangent. And what does that turn into then? Looks like we need another new page, huh? So we got 2 pi. And now we've got the limit as b approaches infinity. And what did we still have there? We had negative, what was it, root x to the 4th plus 1 over 2x squared. Is that right?
Yeah.
Yes.
Yeah. Plus 1/2 natural log absolute value secant theta. And secant theta was our hypotenuse, which was root x to the 4th plus 1 over our adjacent side, which was 1, I believe, right? So
Yeah.
square root x to the 4th plus 1. And then plus tangent theta, which was just x squared. And all of that will be evaluated from 1 to b. Good or no?
Yeah.
Great. So now we've got 2 pi times the limit as b approaches infinity of negative root b to the 4th plus 1 over b squared, or sorry, 2b squared plus 1/2 natural log absolute value root b to the 4th plus 1 plus b squared minus, now we'll plug in a 1 for all of this, which is going to give us what? Negative root 2 over 2 plus 1/2 natural log of root 2 plus 1. Good or no?
Yeah. That's what I got.
Wonderful. All right, so now as b goes towards infinity, let's see. This negative root b to the 4th plus 1 over 2b squared, as b goes towards infinity, this just becomes like negative b squared over 2b squared, which would become like what?
Negative 1/2.
Negative 1/2. And then let's see, what about this? This becomes 1/2. I missed my absolute value there. Plus 1/2 natural log of infinity to the 4th plus 1. So natural log of infinity plus another infinity. Minus all of this negative root 2 over 2 plus 1/2 natural log of 1 plus root 2, which all looked really nice. And we had all these really nice finite values here, didn't we? Except for this one. True?
Yep.
Which tells us that this integral diverges. And so the cool thing here is we've now seen that for this same function from 1 to infinity, way back when, the area is infinite. The volume, if you revolve it around the x-axis, is finite. But the surface area, if you do the same revolution around the x-axis, comes out to be divergent also, and it comes out to be an infinite amount of surface area. So what this is saying is, if I were to take this function, the simple, nice, easy function of 1 over x, and you were to revolve it around the x-axis, there is an infinite amount of surface area, but a finite amount of volume, which seems impossible. Doesn't that seem impossible?
It does.
Yeah. Imagine you have this actual physical object in front of you, right? And you take it and you fill it up with paint. You could put how many units cubed of paint into it?
Pi units cubed of
You could
paint.
put pi units cubed of paint inside of this thing. Now, suppose you take out your paintbrush and you've got this object and you filled it with pi units cubed of paint and you start painting the outside of it. Well,
It
are
takes
you
you
ever,
forever.
you will never, I mean, you will run out of paint before you have finished painting this thing, even if you assume that you are painting it with an infinitesimally small thinness of paint, right? If we are painting it with a thickness of 0, right, so that really it's just the color is being thrown onto it. We don't have enough of this paint that will cover the outside of this thing that we have filled entirely with paint. It's kind of a little bit of a paradox there, isn't it? Isn't that fun and exciting?
Yeah, that's crazy.
Yeah. This particular object has a couple of different names. The one name that has been given to it is Gabriel's horn. I don't know if those of you that are the religious Christian persuasion, you're familiar with Gabriel, right? What does Gabriel do? Those of you that are you Christian folk.
Also, like Jews and Muslims, because
Well,
he appears in all 3 of their religious texts.
I suppose. What is Gabriel most known for, though? That's my question.
I feel like he's most known for coming to like the Prophet Muhammad, right?
All right. What does Gabriel do? What does he have? What does he carry with him?
I have a coworker named Gabriel.
That's unrelated.
I assume he carries a horn with him since that's what we're talking about, but honestly, I
Yeah,
don't know.
he that's something that he does is he is supposedly the archangel Gabriel is the one who like blows the horn to like say the judgment day has come. No, that's not familiar to anybody. No, maybe, yeah. Okay, well, the reason why they call this thing Gabriel's horn is because theoretically, like your judgment day is like the infinite afterlife coming together with the finite existence on this world. And so they've called this Gabriel's horn because Gabriel is the one that comes and merges the two. Or not the one that does it, but the one that blows the horn to say this is what's happening now, judgment day is here. And for the non-religious folk, they call it Toricelli's trumpet. So,
Who's Toricelli?
Toricelli was a was a mathematician in like I want to say the 17th century.
Did he play the trumpet?
I don't know. I know he invented the barometer.
Invented the what?
He invented the barometer
Oh.
Yeah.
Oh yeah.
for measuring air pressure.
Wow.
Yeah.
But is he Seth's coworker though? That's the important part.
I don't believe so because I'm almost positive he was a 17th century mathematician. And so, unless you, I don't know. Yeah, no, I'm going to go with no. No, he is not. Was it Seth's coworker? Yeah, he's not Seth's coworker. Anyway, just an interesting little thing to note there. So it's Gabriel's horn or it's Toricelli's trumpet. Kind of cool stuff. All right.
Does the little like point of the thing as it goes for infinity, does it just become a line then?
Say that again.
Like you know how the graph of this thingy, 1/x, goes toward infinity, and then you would revolve it, and then it gets narrower and narrower, like a small cylinder sort of. Would it just become a line?
Well, no, it doesn't. There's always some space there.
Okay.
The limit as it goes towards infinity, yeah, is 0, but it goes on forever. Infinity is not a number, so we don't get there, right? But that's the whole issue with all of this infinite and finite stuff that we're talking about. Yeah, it's fun stuff. Infinity is a very cool concept. And we're doing, I don't know, when you do calculus, we talk about infinity as if sometimes like it's as if it's a number. We treat it sometimes like it's a number. Like you can even see like in my work here, like I'm sort of treating infinity like it's a number. True. But
Yeah.
we have to keep in mind really that infinity is not a number. And that we're sort of doing, and there's no way to get around treating it like a number sometimes in calculus, but it's sort of a disservice to a lot of the higher branches of math and a lot of the like number theory and set theory stuff. When those of you that are of the mathematical persuasion here that want to really study math long term, it's sort of a disservice to treat it like a number because it's not, but it's effective for our purposes here. There's some really cool things you can do with infinity and different levels of infinity. I don't know, did we talk about the different levels of infinity last year?
Briefly. Yes.
Yeah. So there's lots of different levels to infinity. There's aleph not or aleph null, the Hebrew letter aleph denotes different levels of infinity. So aleph not, aleph null, or aleph not, aleph 1, aleph 2, and so on. And they're an infinite level of infinities, which is kind of also cool. So anyway, we got a few minutes left here. Let me see. Yeah, we're not going to worry about this. We're going to talk about that particular function when we do series. Well, maybe we should. I don't know. Maybe we should. We'll stop there. We'll worry about that a different day.
Can we talk about different levels of infinity after the AP test?
Yeah, sure. We could do some of that. Here's what we should do. All right, let me stop this here for a second here.